Okay, so I want to continue process capability. So here we are in part two. I talked about CP1 barely capable. We talked about CP2, which is probably too capable. I want to add just a little bit more detail about CP equals 1 barely capable. When I drew this here, this was an accuracy problem. So we're losing. So this is going to be an accuracy change because we're shifting our average from our target. So a target versus our average. But here's another one, is that's losing accuracy. We could be losing precision. So in this case, we're going from barely capable and then we can go with any precision loss this time instead of accuracy loss, and we go to a situation that looks something like this, where now we're making both parts that are too large and too small. Our overall accuracy can be good on average, but our precision has spread out. That means that our minus 3 sigma and our plus 3 sigma are out here, which means that process capability is now less than 1. We're no longer even barely capable. So that's an addenda onto the CP1. Okay, so question now is process capability as we have it defined checking for accuracy or precision? Right? Okay. So stop and think about that for a moment. Are we checking for accuracy or precision? Okay, so you can pause the video, think about it, scratch down an answer, and then just pick me up again playing. Standard deviation, is it associated with accuracy or precision? Check the accuracy and precision review, but this is precision. Okay? Standard deviation is associated with precision, because we can have a huge spread on a normal distribution, like a big flat curve. On average, we're making good parts, right? This is we've doubled the part size and we've halved the part size. They're all bad parts. But on average, if we just average them together, it's great. Well, on our process control, our SPC charts, all of that, we're measuring multiple parts. So if we're measuring 6 parts every 2 hours, half of them are double the size, half of them are half the size. Hey, the average is good and we keep chugging along. That's why we also check a range chart, is to check the precision. So X bar charts do accuracy, range charts do precision. We're checking them both. The tolerance is defined, it's not changing. So what are we doing? We're checking precision with a CP. So our addendum to this process is called CPK. This is a process capability for an off-center process. That means when the average of our production, so our process average, our X double bar, is not exactly the same or extremely close to our target. This is essentially the same idea, except we're going to do a minimum function, and we're going to do a CPU for upper, and it's going to equal our upper statistical limit minus our process average over 3 sigma. And we're going to include in our minimum function a CPL for lower, which is going to be our process average minus our lower specification limit over 3 sigma. So what I've done is I've taken our CP and split it in half down the middle. So now we're looking at instead of, say, our upper specification limit, lower specification limit. If I ever say control limit yet in the video, sorry, it's all specification limits here. Towards the end, maybe I'll comment on X bar charts, which would be control limits. But okay, anyway, here's this. If we're looking at our CP, we're doing the full standard deviation. But now if I come in here and say add only looking at half of this, we're comparing our, here's our X double bar, right? So we're comparing, actually that should be dark. This would be for CPU. This check is going to be for CPL, whereas the whole range is for CP. We're just breaking it into the two halves. Okay, so what we're going to do is we're going to do both of these calculations, and then we're going to do the minimum. So our CPK is going to be the minimum, or whichever smaller is the value of CPU and CPL. So that's what the minimum function does, is it says I got two values, or however many values. In this case, it's going to be two, a CPU and a CPL. Pick the smallest. Why the smallest? Because small CPs are bad. So we're picking our worst case scenario. Why are we doing this? What we're going to do is we're going to consider a case where I've got, this is on center. That means our process capability, our X double bar, is right here with our target. We are in the center of our LSL and our USL. So our normal distribution is centered in between our two tolerances. This is great. We follow the math here for the example they're giving. I'm not going to run through it or ask you to run through it here, but CP is 2 and CPK is 2. Okay, so here doing our CP and our CPK doesn't matter. Where it matters is if we start to come in here and add on. Okay, so Let's say we're shooting for 50. Well, look, now I'm off. My accuracy has changed, correct? I'm not spreading my curve out. I'm not changing my standard deviation. I'm just shifting my curve sideways. Well, so in this case, as we shift our curve, in this case towards higher values, CP does not change, right? So our standard deviation is this value. Our tolerances are this value. Our tolerances are twice the standard deviation. Okay? So, or twice 6 sigma. Sorry. Okay, so our standard deviation isn't changing, but our process is drifting, right? We're getting larger and larger parts. We're maintaining precision, but our accuracy is off. So now we're maintaining precision but losing accuracy. Eventually, we go to a situation where we've got possibly half our parts are now out of tolerance, right? That's this situation. Here's our upper specification limit. CP is still good. CPL or CPK is 0. Okay? If we're really pushing our luck, we go to a situation like this where we even get negative CPK values. Here's the trick though. CP is still 2. It still says our process is capable. Well, here's the trick. Our process is capable, right? This is capable. If we just recalibrated our machine, reprogrammed it, reset it, did something, we shift this back over, and our process is capable. There's that key word. Don't miss it. It's capable of making good parts, but we're offset. So the one-sided value here shows us that. Okay, so let's take, let me back up, and let's do an example here. Okay, let's take this and do this as an example. We've got, in this case, a process standard deviation of 2, whatever it is. 2 inches, 2 pounds, 2 millimeters. Our standard deviation will be the same as the measurement we're taking. So whatever this measurement is down here. Let's say it's pounds of dog food in a bag of dog food. Okay, right. So we'll stick with our example that it's in pounds, but well, so I want a 50-pound bag of dog food. Okay, and I'm getting values from, at the extreme edge, 44 to 56. I don't know if I'd be happy with buying 50 pounds of dog food and actually getting 44, but let's just run with it, okay? Well, so let's say we're willing to sell between 38 and 62. Okay, it's not a good example, but let's run with it, okay? So our USL is 62, our LSL is 38. Well, let's do our CP. So remember, these numbers are defined by design. The corporation is defined these numbers, our specification limits. The process itself, we have to go measure sigma. Sigma should be measured by the real process in the facility. So what do we get? We get USL minus LSL over 6 times 2. Right? So, make sure that works. We get 24 over 12 equals 2. Okay, so that is a very capable process. Now, let's go and shift the gears to what happens if we're off center. Okay, let's just go to the extreme case right here. Let's go to the extreme case where our x double bar equals our upper specification limit, and they both equal 62, but sigma still equals 2. Same precision. Okay, now we do our math for CPK. Okay, so CPU equals our upper specification limit, which is 62, minus our process average, which is 62, over 6 times 2, which, by the way, CPU is 0, right? 62 minus 62 is 0. 0 divided by 12 is 0. CPL, we don't even need to do this, but we're going to do it. It's our process average, 62 minus 38 over 6 times 2 equals, and lo and behold, should be the same thing. 62 minus 38 is 24 over 12. It's 2. Now we take the minimum of those two. Let's see, we got 2 and 0. Which one is the smallest? It's 0. So our CPK equals 0. So what does that tell us? That tells us our process is at best only half capable. So this is half capable. We're literally producing half bad parts. Yuck, right? Okay. So that's an example of doing CP versus CPU. Okay, so why check CP at all if we've got CPU and CPL for CPK? What do you think? Let's do this. I already asked the question, and we're trying to answer it. Is CP checking accuracy or precision? And we already decided it was precision. So we already said CP is a precision tool. So just like we have an X double bar, or excuse me, an X bar, we have an X bar chart and an R chart in statistical process control. One checks for accuracy, one checks for precision. CPK is primarily looking for accuracy. So CP is looking for precision, CPK is looking for accuracy. Big important statement. Bigger marker. CP answers can the process produce good parts? So based off of our tolerance that we set, can the process. CPK really answers is the process making good parts. Let me say products. Right, so if we've got standard deviations for the different processes available in our facility, an engineer that's doing design can give us a tolerance and say what processes can we use to make this product. Well, we can go through and do the calculations and say, based on process capability indexes, these are the processes, X, Y, and Z, that can be used. Y is cheaper than X and Z. They're all capable. Go with Y. Okay? Or Y is the cheapest, but you know what? We have a lot less injuries per part produced or per thousand or whatever using Z, and Z is only barely more expensive. Let's go with Z. Something like that. I don't know. Or maybe one produces less environmental waste or something. You could find reasons other than just costs and precision. But then notice that in the CPK calculation, this one required X double bar. We have to be making parts to find this. We don't have to be doing production to find CP. Yes, we needed to have done previous production or have a good idea of the standard deviation for a process, but this requires us to actually be making the product and measuring it to get CPK. So, does CPK check for precision? Yes, it does, actually. So we use CP for product selection. We use CPK as the quality control check during the process. Okay, so let's see. That being said and done, we could go in and compare this to process control charts. Right, we can come in and say, well, I'll tell you what, I'll do that in another video. Let's stop this one and I'll come in and do the next one.